Michael got his PhD in geography from the University of Toronto, and for the last 15 years or so, he's been doing research into how to characterize pollution exposures to population exposures, to air pollution, and how to assess the associated health effects, and has published some of the most widely cited papers in the field. His interests are wide-ranging, in addition to focus on the long-term effect of air pollution on cardiorespiratory diseases. He has also studied the contribution of the built and natural environments to sedentary lifestyles and obesity, and his approaches are novel. He is currently funded by the NIH on studies that use cell phone sensors to obtain personal monitoring information on physical activity, air pollution, and geographic location. So Michael's here today. He's visiting for Nestle ACD for a couple of days with his PhD student, Colleen Reed. And we're exploring collaborations that can help transition our air quality observational and modeling data into the health impacts realm for decision support. So this is where we hope to build some collaborations. So today, Michael will be speaking on comparing remote sensing, atmospheric chemistry, and ground-based estimates of fine particulate matter on survival.
Thanks very much, David, for the kind introduction. It's really a pleasure to be here. It's always nice to speak to an audience where I don't know everyone, because I always learn something from the questions. And because I recognize a lot of the material here might not be very familiar to you, I would encourage you to ask questions as I go along if you want clarification, rather than waiting until the end. I'm going to give you some broader background to the field of air pollution epidemiology, and particularly mortality studies. And I guess the first point is that airborne particles less than 2.5 micrometers in diameter can penetrate deeply into the lungs and the small airways, and they're biologically toxic agents that are linked to a wide range of diseases and potentially premature death. And I'm going to show you more on this in a minute. And the societal costs of complying to regulations for PM control are huge. They're estimated to be about $100 billion per year. And as my friend Dan Costa of the EPA likes to say, in any given year, the benefits, the monetarized benefits of all government regulations, so flight safety, food safety, drug regulation, all of the benefits, PM accounts for 60 to 70% of those monetarized benefits in any given year. So this is a big issue societally, and as a result, there's a lot of interest in trying to get the estimates of exposure and health effects right. And this was a study that I published, way back in 2005 now, where we looked at air pollution mortality in Los Angeles, and we found that the dose response in Los Angeles was nearly twice as big as it was in the rest of the country. And this was picked up by a lot of the popular media because it had such big societal implications for how much we could regulate air pollution, whether or not the Clean Air Scientific Advisory Panel was giving the right advice, or the EPA administrator was listening to that advice, and whether or not the estimates of deaths were actually correct. So we've known for some time now through the London fog incidents, and my colleague Rick Burnett, who gave me this slide, pointed out, I said to him, Rick, I think you've got a typo because it says 1962, not 1952. And there were actually many London fog incidents, not just the famous one of 1952. And the levels here you can see, it's an inferred level from the British black smoke estimate, but at some point you're hitting 2,000 micrograms per cubic meter of what was probably a very highly toxic mix that contained a lot of carbonaceous and black carbon materials, or organic and black carbon materials. And you can see here very clearly that the death rate goes up in sync with perhaps a little bit of a lag after the PM. And the famous episode in 1952 had something like 12,000 excess deaths, and this had about 10,000. And these are levels that are being seen, or almost this high, in Beijing, China today. Pardon me? well, the deaths are unknown, but the PM levels, we're seeing 800 micrograms per cubic meter. This has probably got, I'm thinking it's, it goes up, the British black smoke metric, and correct me if I'm wrong, it goes above PM 2.5, so you're going to have some larger fraction of particles. So if we were to actually infer the PM 2.5 from this, it would probably be about half of what's there, roughly. It goes up to 0.4, 0.5, something like that, or yeah, 5 micrograms, or 5 micrometers. So it's probably, what were the peaks in Beijing? They're around 800, 900 right now. So probably in about the same range. And the health response, in all likelihood, is fairly similar, although I haven't seen any studies that have been able to document that. So this is a bit of a rehash of what Colleen showed this morning, but I realize there might be some people on the web or in the audience who weren't here this morning. So I just wanted to emphasize the biological pathways that bring us from particulate matter exposure to cardiovascular disease. And by far the most important one that we know of goes from particles penetrating deep into those lower airways in the alveoli where the blood exchange occurs with the oxygen, leading to pulmonary oxidative stress and a subsequent immune-like response that causes inflammation in the lung. This leads to systemic oxidative stress and inflammation. So it begins to spill over from the lung to the cardiovascular system, so it's called cardiopulmonary inflammation. It's possible, too, that we're also seeing some autonomic nervous system reflex that's being triggered that causes impacts on the vasculature, the blood platelet aggregation, and the heart rate variability, all of which could increase the potential for arrhythmia. And then finally, some direct penetration through the, blood barrier. So you're getting constituents that are going directly into the blood, and those might be ultrafine particles, soil metals, and organic compounds, again affecting the vasculature. There's less known about this pathway, but certainly the animal study suggests that a lot of the very small particles can penetrate into the bloodstream. Now, one of the important things that will show up in our story today is that it's not just about mass when we talk about PM health effects. A lot of it is about the composition and the interaction in time and space between where the people are and what the pollution levels are at a given time. So it's entirely possible that fairly small increments in terms of PM mass might be highly toxic, and those might be attributable for a relatively larger proportion of the observed health effects. Yes, there is some clearance that occurs, but many of them do penetrate down that far. No, not that we're aware of. I mean, as they get smaller and smaller, the particle numbers go up. And there's still controversy about how they affect the lung, whether or not it's like an immune response, whether or not it's adhesing toxics. They have a lot more surface area per mass, so their potential to deliver toxins deep into the lung is at least conceptually greater, but it's still an area of active research. So the other reason that when we look at mortality, it's very important, is it really pushes the cost-benefit analysis that we see. So the value of a statistical life, in Europe it's less. They use about 3 million euros. In the US it was about 6.5 million. I think the US EPA has just increased it to around 8 million, so it's closer to what we use in California. But even at 6.5 million, you only need 154 deaths to have $1 billion of potential benefits. So if you're adding this up over a very large population in the United States, you can quickly see how you might exceed that $100 billion compliance cost, and how getting the dose response right is very important. And when we look at the mortality estimates that we get out of the long-term studies, these often dominate regulatory decisions because they are much bigger than what we see from the acute response. So predicting them accurately is very important to protecting public health. And here's a nice plot that my friend and colleague Nino Kunzli who did his PhD with now retired Ira Tager at UC Berkeley, did to conceptualize it. So we have a larger group of deaths that some of which are not attributable at all to air pollution. And then we have, sorry, this pointer is a little stochastic, but there we go. Then we have the short-term effects that are probably operating through that autonomic nervous system disruption, arrhythmias, and maybe some respiratory effects like asthma attacks. And then we have these longer-term effects where we might expect to see the formation of atherosclerotic plaques and the development of heart disease, some of which would overlap because they'd make people more susceptible to short-term effects, but many of which would accelerate the process of dying on their own. Yeah, the yellow box is just all deaths. Yeah, so this is, the universe of, you could think of accidents and injuries probably not being associated with air pollution. Although there is evidence now that disruption of the vasculature can lead to depression, so maybe suicide is linked to air pollution. But I'm not going to go down that path and try to defend it, but I have heard that suggested. In a recent assessment that was done by the World Health Organization and published in the leading British medical journal, The Lancet, in December last year, they looked at 67 of the major risk factors. And when we look at particulate air pollution, it's quite remarkable. And a lot of this was due to having atmospheric chemistry type models that they could then start estimating in rural areas where a lot of big populations live in China and India and other places in Southeast Asia. You can see that air pollution is the number 9 cause of premature death and disability. And it's estimated that there are 3.2 million deaths attributable to air pollution exposure per year, and about 76 million disability-adjusted life years. So these are measures where people are not living life to the fullest, where they maybe have a disease, and it's reducing their quality of life. So certainly a very big public health issue, and again, the studies that derive these estimates are important. Now, although they're important to do these studies, they're very complex, they cost a lot, and there are very few studies that look at long-term mortality available. The one that I'm going to talk about today is probably the most famous, the American Cancer Society study. There have been a series of studies done in Europe and Canada and a few others in the US using smaller populations. But I would say the results are mixed. We don't always see consistent effects on different outcomes, say respiratory versus cardiovascular disease. We don't always see effects that are statistically significant. But one thing that we do see, there's a general pattern that the more precise we get with our exposure models, so getting better estimates of exposure seems to have a tendency toward bigger effects. And that's what we would expect from statistical theory. Statistical theory tells us that if there's non-differential measurement error and we're trying to assess a health effect, that we're going to see an attenuation toward the null as we have larger measurement error. So if we look at spatial epidemiology and environmental epidemiology and air pollution, we've seen an evolution, I think, toward trying to get small area estimates and get them more accurately to where people live. So this is the first map of the American Cancer Society cohort. And essentially, all that was done here is they tracked about 500,000 people for, at that point, 6 years. And they compared exposures between Phoenix, Los Angeles, New York, and other places. So it's just simply what the central monitor is in one city compared to another. Now, as atmospheric chemist, is that a very satisfying approach? Or I'm seeing some, yeah, probably not. But it was enough to show that there were probably significant effects, and because we would expect to see them biased toward the null, our suspicion was that they were probably larger than what we were observing in that study. There were some other studies that came out of the Netherlands by Gerhard Hoek and Bert Broonkrief that used road buffers. So they just looked at people's distance to the roadway and where they lived and tracked their survival. And they found that death rates from cardiovascular disease or a well-controlled study where they controlled for smoking and many other things more than doubled when they lived within 50 meters of a major road or 100 meters of a highway. They haven't done any estimates about what it's like to work beside a big freeway, so don't worry. You're inside most of the time anyway, right? So air conditioning. There are several studies that have used sort of basic interpolation, so spatial moving averages. Here's just one example from a study I did in Los Angeles of sulfate levels. And you can get a general pattern of the gradients that's going to be better than just measuring between cities, but still not very satisfying. And then this is from a land use regression model that I did with my colleagues Jason Su and Michelle Willem in Los Angeles. And here we put out 200 monitors, so we really saturated the area twice. And then I'll show you a little bit more about the statistical model later. But we used the pollution measurements as a dependent variable and then used traffic and other variables to predict. And what that allows us to do is to get very fine-scale predictions, which are going to capture that potentially toxicologically active component that comes out of traffic. So if we look at the literature, then there are very few studies that have used refined exposure models that actually, with the specific addresses of where people live, and it continues to raise questions about the validity of the results due to poor exposure assessment. And we're seeing now growing availability of great atmospheric models coming out of NCAR and other places, remote sensing, and what are known as hybrid models, where we're going to try to combine, say, remote sensing and land use regression. And these are important innovations. So in that context, we wanted to try to look at, well, what could we do to essentially fill in some of the missing spatial information about exposure variability for larger gridded, like remote sensing predictions, say at a 10-kilometer grid. And then how can we use that and to predict mortality in the United States? And then finally, how does it compare between different models and approaches? So would we actually see where the exposure model has a big impact on the size of the risks? This is sort of a schematic of the process that we followed to develop the PM 2.5 model. So we assembled all available data from federal reference monitors in the United States. So about 1,460 monitors. We did sort of standard averaging techniques. We derived land use around those. We took remote sensing estimates that were provided to us by Randall Martin at Dalhousie University of PM 2.5. We used a machine learning algorithm in combination with this land use regression estimate to get monthly estimates. We took the residuals and then combined them. So we did a space-time algorithm to smooth the residuals. We combined them post hoc, cross-validate against leave-out sites, and then assign to about 670,000 people. So let me give you a little bit more detail on that. This is the array of monitors that are available in the US. And we're really fortunate to have such a rich data set. And then these were the stars are the cross-validation sites that we just drew at random. It's about a little more than 10% of the data set. We went to a lot of trouble to assemble traffic data, and we purchased it from a company known as TeleAtlas. They have something like 40 million traffic points collected across the United States. We're very interested in that. We're not able to capture things like congestion, but we are able to capture each one of these as a separate traffic count. So we took this and imputed it to the roadways where we didn't have full traffic counts based on the functional road class and the county-wide average. And I know for emissions modelers that there might be issues with that, and we're working to improve it. But this gave us what we like to think of as a road length that's weighted for traffic density around the monitors. We took the National Land Cover data set led by the USGS to get things like open areas. You can see Los Angeles is not a very green place. And this is Randall Martin's retrieval, which is based on 6 years of data from 2001 to 2006. You're picking up the variability that is very consistent with the monitoring network. the industrial Midwest, the Northeast, Southeast, and then, of course, parts of Los Angeles and the Central Valley in California, and I guess the Wasatch Valley in Utah. So we took this, and based on a review I did back in 2005, where we looked at available pollution models that were good for doing health studies. And that's different than trying to look at estimating for our interest in where pollutants are in the environment or emissions, but we actually want to be able to predict over small areas. And one of the methods that comes up well on many evaluation criteria is called the land use regression modeling strategy. So here we've got the monitor values, and they're used as a dependent variable with approximate land use, traffic, and population and physical geography variables. So we're using these monitoring data as our Y variable. And then we would extract out, say, the length of major roadways, and that becomes one of our predictors. And we build our model from there to try to optimize the prediction so that we can get these small areas. And because we have the land use and the traffic everywhere, we can do what's known as an interpolation with auxiliary data for areas where we don't have monitoring data. So we put this through a machine learning algorithm known as a deletion, substitution, addition algorithm. So this essentially takes every combination of variables, takes 9 folds of the data, so it breaks the data into 10 folds, takes 9 folds, fits a model, cross-validates on one, goes on, says, if I add another variable, do I improve my cross-validation accuracy? And after we went through that process, we ended up with 2 fairly simple models. One of the interesting things, too, and this is perhaps something that you would have already known if you worked a lot with remote sensing, is that we couldn't put remote sensing and traffic in the same model. So there seemed to be such high collinearity between them. And the remote sensing, according to Randall, probably is picking up differentially darker particles, which we might expect to be associated with traffic more so than some of the other constituents. We're still not sure why, but certainly the remote sensing seems to be associated with traffic because we can't put the 2 in the model. And these models will accommodate highly collinear. So this is a generalized estimating equation predicted by the month. And we have one model without remote sensing, which has our traffic weights within 1 kilometer of the monitors, and then a measure of green space within 100 meters. And the green space here is really just a proxy for lack of emission sources. Or that's how we interpret it, at least. Then we have another model which has the squared and cubed terms of the remote sensing, and then developed land areas within 200 meters. And this is really built, for built-up areas, a proxy for emission sources. Now, at Colleen's talk this morning, there was some question about, well, how important were the different variables? And this just shows what's known as a cross-validation risk. So this is predicting the monthly average, and the average risk means how much error we have by the month. And, sorry, this pointer is, there we go. This is for the model without remote sensing, the model with remote sensing. There is the cross-validated risk as we put the remote sensing in the model, and then the second variable. So it's absorbing almost all of our explained variability. And we get to this third variable, which is the developed land area, and then it's basically noise after that. This is the model with traffic, and you see traffic doesn't really drop the cross-validation that much, and then we put in that third variable, green space. So we're really just getting a very marginal improvement. But the remote sensing is a very big predictor. Now that doesn't necessarily mean that it's what we want for a health study, and I'll show you what I mean there in a minute. These are the plots of cross-validation when we show with remote sensing, without for traffic. And you can see that really the land use regression is not picking up a huge amount of the variation, but it's when we do the space-time kriging afterward that we're really getting a lot more variability. Sorry, I think this is it. Yeah, maybe I'll just use a stick. So this is after we apply a space-time kriging model, which in the interest of time, I'm not going to go through in detail. But suffice it to say, it's essentially using the correlation and what we don't predict well from our models and in time and space to predict those monthly averages. So we get a very good cross-validation here against the leave-out sites where our cross-validation R-squared is something like 80%. But now this is where I think it gets interesting, and it gets to the crux of, moving forward with collaborations with atmospheric chemists and health scientists. Clearly the space-time kriging is doing a lot of the heavy lifting here, but we're getting a lot out of the remote sensing. That's probably important. But here's the predicted surface that we get from the remote sensing model that fuses the Bayesian maximum entropy space-time kriging along with the land use regression. So that's Los Angeles, Chicago, and Atlanta. And we've just tried to, you're getting some variability, but it's all at that, 9.8 kilometer grid. And if you look very hard in here it's maybe more apparent. The developed land area is giving us within grid variation. I don't know if you can see that from back there, but there is some within grid variation, but really not that much because this is so dominated by the remote sensing retrievals. Now, when we use the traffic, you can clearly start to see this is the road network, which for anybody that's lived in Los Angeles becomes a nightmare in your dreams. Which traffic route do you not want to take at what time? I lived there for 3 years. Wonderful place except for the traffic. But anyway, so you can see that we're picking up this very fine scale variation that's close to the roadways in all three of these major centers. So it's potentially giving us this within city variation that is highly associated in many other studies with health effects. It's coming from traffic constituents, which we're not getting when we use the remote sensing. So if I could summarize the exposure modeling, the remote sensing certainly dominates when competing against land use and traffic. So our SUR squared was 60% for remote sensing versus 27% for the traffic. Both models achieve very high prediction accuracy once we use the spatiotemporal interpolations. But the small area variation is probably important, and it's not being picked up very well. Sorry, I must have put that in. Mistake. It's not being picked up very well when we use the remote sensing estimates. So moving to the second objective, looking at the health effects and comparing them. This is building on the American Cancer Society study, which I've been working on now for about 15 years, and some of my colleagues for considerably longer than that, almost 20 years probably. And in our previous studies, as I mentioned, we just used between city contrasts. This was the first time that we went into the data set and we geocoded everyone to their home address. So we end up with 669,000 individuals in the study. We've got 105,000 deaths from circulatory causes. I'm going to focus on circulatory causes for this talk because it's more about illustrating the importance of the exposure model than deriving the primary health benefits. And we've got control here for a lot of potential confounders, smoking, exposure at work, and I'll show you more on that. But this is a really big issue, and this became the source of a lot of controversy when EPA was first using these studies to regulate, because people that didn't want to pay for the regulation said, it's not that there's a lot of sulfate and pollution in the Ohio River Valley. It's that a lot of people smoke and drink there, and you haven't controlled for that well enough. So we did a very major reanalysis of the first study, did just about everything we could to torture the data, and the health effects persisted, even when we controlled for many more confounders. But this is a big issue as we look at epidemiologic studies, and I'll show you a little bit more on that in a minute. So in total, we control for 44 individual variables and 8 ecologic confounders in what are known as multi-level models. And so this is, I think, one of the first big advantages that you can see from using the broader atmospheric chemistry, remote sensing, or these hybrid models. The crossed circles show where we were previously able to do the study. So it was only in those areas, and we had just under 500,000 people that we were able to study, and now we're able to study all of these areas. So what we're doing, in essence, is we're really increasing our coverage of the US population, and we're increasing our our potential to detect low exposures to high. And when you're doing an epidemiological study, you want to have exposure variation, because without that, it's going to be very hard to differentiate high and low and to estimate your health effects. When we think about confounders, certainly cigarette smoking is a big one, still one of the major causes of death globally, and still a much bigger risk factor than you might expect in the United States. These are all the variables that we've included. They're in this survey that's available with the American Cancer Society. Now, I've had people say, you really haven't done a good enough job controlling for smoking. They're probably right. We don't have blood measures or swabs from the person's house that give nicotine. So, there are issues with this smoking information, but it's certainly better than most studies, and I think enough to allay concerns that we don't have control for that confounder. We've got variables for education. There are many studies that show having higher levels of education increases your survival. Marital status. Married people tend to live longer than single people or divorced people. I like to joke and say that, on most days being married is good for you. Most days. BMI and BMI squared. Why squared? Because there's also an effect of being underweight. So we have to have that quadratic term, so the sort of a U shape where they're really underweight or really overweight is worse for you. Alcohol consumption, in moderation, good for you. Excessively, not good. We've got occupational exposure variables that I think are among the best that you could possibly derive from a survey. We had two leading occupational epidemiologists, Jack Simeonticki and Mark Goldberg, go through, and they created an occupational dirtiness index based on 156 job categories. We also had direct questions on exposure to diesel, stone dust, coal tar, and those types of things. And then there was a good dietary index. I'm not sure, it must be a conversion problem on the projector, but we've got different quintiles that show consumption of vegetables, citrus, high fiber grains, and fat. We also looked at the possibility that the neighborhood in which someone lives is going to affect their health. And there's a big literature on this. It's called contextual environmental effects. So living in an area that is poor, even if you're wealthier, is probably not good for your health. And there are many reasons for that. You may not have access to good infrastructure. If there's high income inequality, it might promote the so-called invidious comparisons. But nonetheless, we took all of these, and this just shows you why it's important. This is from that Los Angeles study that I talked about at the beginning of the talk. And this is the PM level. I'll just focus on the one where we've assigned it to the individuals in the study. This is the PM level and the median household income going back to the 1980 census, which is close to when our study subjects were enrolled. And you can see this clear relationship, where as income goes up, the pollution levels tend to go down. And if we look at something like households with air conditioning, we can see that the proportion of households with air conditioning goes down generally as the pollution levels go up. We don't have as many people down in this end, so I wouldn't trust the curve. But so their potential to protect themselves from penetration of the pollutants into their house is partly being influenced by the neighborhood in which they live. So we took all this information and we put it into what's known as a Cox proportional hazards model, or what's more generally known as a Cox survival model. And this model has been importantly extended by my colleagues Ed Hughes, Renjin Ma, and Rick Burnett. I've been working with them for many years. We have a software program that I can share with you that was funded by the Centers for Disease Control. We've been developing and training some of their staff on it. But essentially, we're looking at people having a hazard function. So this is, you can think of this as the instantaneous probability of dying at any point during the follow-up between 1982 and 2004. And that for every group of people within a certain age, race, and sex, there's a baseline hazard. So I'm always comparing, 45-year-old white men against other 45-year-old white men, and then I'm summing up over all these different groups to get some baseline hazard that's shared. And then I have risk factors like air pollution that I'm interested in estimating, or smoking, which I'm going to indicate through beta, this beta, and then the XJ. And then what's special about these models is we have this eta J term. And this eta J term is essentially the residual of mortality that's not well explained by the fixed predictors in our model. And it has an expectation of 1 and a variance of 0 when we perfectly explain the survival of all of our individuals. So what we can do, and I won't go into it in detail, I don't have time to explain all of it, but we can actually take the residual mortality, in this case by the county, and map that out to see whether or not we have any residual mortality that's not being well explained by our model. And if it clusters in space, it's suggestive that there might be a missing variable or a group of missing variables that we haven't modeled too well. Now, and so far, we're doing a pretty good job with all these variables. We don't have a huge amount of residual variation in our eta J terms. So the other exposure models we use, I showed you the main one that we developed, the hybrid model. We use the remote sensing by itself, which is that surface that I showed you from von Dockler and Martin. That's about a 9.8 kilometer grid. We used a simple Bayesian maximum entropy space-time kriging model, which runs at exactly the same scale. We've done another paper, the Lee et al. Paper. Sanjay Lee is my former postdoc, and we compared remote sensing to the ground-based estimates. And then we took a product that was developed as part of the EPA's efforts to inform the Environmental Public Health Tracking Network of the CDC so they could have a nationwide exposure model. And it's essentially a CMAC type model, so community multi-scale model that oscillates and calibrates to the ground level. So it's a form of data fusion so that essentially where there's more ground information, the ground is given a higher priority in the estimation and it scales. Where there's less ground information, the CMAC model is given more weight. It's a very long paper that Holloman produced on this in environmetrics. Very good. I'm not doing it justice now. But when we look at the EPA surface, we can see that it essentially looks something like this. Very similar to our remote sensing estimate, although in this case the grid cells are 36 kilometers. EPA does distribute this for the eastern half of the country at 12 kilometers and then the western half at 36, but we didn't want to introduce differential exposure classification errors. And then this is the Lee model where we've just used a smoother over those 1,460 sites in space and time. I shouldn't say just, because it was really hard to fit this model, because as atmospheric chemists, I'm sure you know, well, let me ask you, when is pollution, particulate air pollution on the East Coast, always the highest? And why? In general, like by season, let's say. No, it's normally summertime, right? Because they get a lot of the sulfate formation in the east. So we see higher levels in the east in the summer. And then in the west, we tend to get the boundary layer crushing down, and there's a lot more wood smoke and heating contributions, so you get higher levels in the winter in the west. So it was really hard to fit this model because you had this, we ended up using this function from mathematical geology called the whole cosine, which allowed for the oscillation from one end of the country to the other, where it's high in the summer, low in the winter, and then it reverses. So the big question is, all this modeling, when we apply it to this very large data set, does it make any difference to the health risks? And the answer is yes, it absolutely does. And we see, just to begin, over to the left, I don't want to just start from the left because I'm from Berkeley, but it's also, I think, the most striking result. There are two sets of results here. One is just controlling for individual risk factors, the smoking, the drinking, marital status. And then this one has the ecological confounders from the neighborhood. And those ecological confounders, interestingly, in this case, tend to increase the size of the dose response. So they have a positive confounding effect. We can maybe discuss why that happens later. But here's the remote sensing estimate. So this is what's known as a relative risk. So here we're comparing the risk of mortality, or during the follow-up, for people in, say, 10 microgram per cubic meter increments. So going from 10 to 20, 5 to 15, whatever increment. So we're always comparing lower to or higher to lower exposure, and then saying, do we see an excess risk of the hazard of dying during that period? And the hazard ratio, in all cases across all these models, is positive. And if it was going through one, we would say it's not statistically significant. So we see what we've seen in other studies, that we do have this positive, statistically significant effect. But here's the size of the effect for remote sensing. It's about 5, maybe 6, 7% for cardiovascular or circulatory deaths. Plus, we now include diabetes in with circulatory because it's all part of what's known as a cardiometabolic syndrome. So they follow many similar pathways. And this is, moving over here, here's the EPA's product. So we see effects that in some cases are about double what they are from the remote sensing. And here it is with just the space-time smoother. They get bigger again. This is the remote sensing being fused with the land use, about the same size as what we get out of the straight smoothing model. And then this is the model that includes the traffic variable plus the other land use variables, the green space. So we go from, if we just look at the individual variables, we're going from a 5% increase to about a 15% increase. And if we were doing cost-benefit analyses, this could mean many, many more thousands of deaths that would be attributable to air pollution. So the question is, why is that happening? Why do we see this variability? Well, one thing, and I've got some prepared text, but all of these models have some ground information. This is the only model that doesn't. And when we look at the correlations between the models that contain ground information, they're generally in 0.8 to 0.9. So even though this model and this model use very different mathematical properties, this has got an atmospheric chemistry model that's been fused to the ground. This one's using the traffic. The correlation between them is 0.86. So they're predicting at these leave-out sites very similarly. But when we look at remote sensing, the correlation of remote sensing to any one of the others doesn't ever go above 0.64. So it's considerably smaller. If you're thinking R squared, that's going from 40% variability to something like 60% explained variation between any one of those two models. So this is the ratio if I'm comparing. So think of this as the increased risk of death. So let's say over here, it's a 15% increased risk of death comparing people, say, at 15 micrograms to 5 micrograms per cubic meter in their PM 2.5 exposure, while I control for all of those other variables. No, the baseline group can be estimated at anything throughout our dose, anything that's within our range of exposure. In this case, we get levels that go down to, by the month, we're down to 3 micrograms in some of the rural areas, and then it goes up over 30, 35 in some areas. Yeah, we've done tests of linear. It's a good question, and this is still a work in progress, so we haven't done all the plots of dose response curves. I can show you what they look like in some of our other studies, and we don't see, at least for PM, any significant deviation from linearity. It generally follows a straight line throughout the dose response. So what we're seeing here is, that the models that, so does that answer? Sorry, I know that some of this is kind of calling. Yeah, it's 10 microgram against all of the. Now there are some issues with that because there's slight differences in the range and the mean, and we could have presented them all across their interquartile range, which maybe would have been a better comparison across all of them. But in sort of a convention in epidemiology is we kind of round to something that seems real. 10, but this often gets used in health effects literature. There isn't that big a difference because they are all fairly similar in terms of their distribution. So we do see that all the exposure models indicate an association between earlier death or loss of survival and PM 2.5, that the risks are varying by exposure models. And the largest risks come from the models that seem to detect this small area variation from traffic. And it's suggestive that our exposure models, if we're going to get proper inference for health effects, probably need to be able to predict at fairly fine scales that often go well below what are produced in standard atmospheric chemistry or remote sensing models. So this is a big challenge for atmospheric scientists, and something that I think you're up to the task. I have confidence that, given some thoughts about this, but it's also, I think, not just about predicting at the fine area, but can you predict certain constituents as well? Because certainly when we look across PM, the toxicological literature suggests the ultrafines, the organic carbon, the metals, these are probably some of the bad actors and things that you would want to be able to predict for a health study. So we're working with Randall Martin to get more highly resolved remote sensing estimates. He thinks it's going to be about a year until we have 1 kilometer estimates available from his new models, which, he's certainly delivered a lot of great material in the past, so I have no reason to doubt that he'll do it again. We're improving the estimates of traffic by implementing a massive network kriging model. It's part of my student Bernie Beckerman's thesis to try to take those 40 million points and interpolate them along the network. And then we're incorporating co-pollutants like ozone. And I can say that using the EPA's hierarchical Bayesian model, we are getting much larger and more significant effects so far for ozone on mortality than what we've seen in the past. And the interesting thing about that is that when we've just used monitoring sites, they tend to be highly correlated. R value is like 0.7 between ozone and PM 2.5. The atmospheric chemistry models seem to break that correlation so that they're not very highly correlated, and we're able to get separate effects in our models and estimate both PM and ozone together. So there are a lot of people that contributed to the funding and a lot of co-investigators that I want to thank. And I want to thank you for having me here today, and Gabby for organizing our visit, and David for inviting us. I want to thank you for your time.
Thank you very much, Michael. Do you have any questions? Chrissy.
What are some of the environmental conditions that you control for? I mean, the personal.
Yeah, good question. We have in the past, we looked at a suite of about 28 different environmental conditions: elevation, maximum temperature. In this study so far, we haven't included those. And I think one of the things we're particularly concerned about that we've seen some indication in the past is the elevational effect. And I hate to say this, when you're in a mile-high city, but being at a very high elevation apparently is harder on your heart. So higher elevation is associated in some instances with higher levels of cardiovascular disease. It's also associated with generally lower levels of air pollution. So we're concerned about the potential there of having what's known as negative confounding. So we have a positive risk factor that's not in the model that's associated with low pollution levels. So we might see higher pollution levels or higher risk estimates if we were to control for elevation, because it's going to have that low pollution, high disease rate. But yeah, we did look at a lot of climatological variables, the availability of medical care. Trying to think of some of the other pollutants. But in most of those cases, it was measured on a county-wide basis because it's hard to get that. So it wasn't a very good measure, but we did test all of them. And the only two that came up in our earlier studies were elevation and water hardness, which again is associated with cardiovascular disease. So, but that when we did further investigation, we were able to eliminate that as a confounder. So we haven't included it in our subsequent studies.
Can I ask a question on the, with respect to the limitation of the remote sensing data, where you show the data with, where it's using the ground information comes out generally more consistent. Do you think is it a limitation of the horizontal resolution? You mentioned getting this new data that's at 1 kilometer, or is it a limitation that you're essentially using column data from the satellite, which doesn't intrinsically give you a concentration estimate at the surface like the surface monitoring sites will?
Yeah, I think in subsequent work that Randall's been doing, he's been using some LiDAR instruments to better control for what's in the column and what level, and it seems to be improving the prediction. So that's some part of it. And then in Colleen's talk this morning, she pointed out that in some parts of the country that are highly reflective, the models don't perform well. So in a lot of the Southwest and in a lot of areas with mountains, they're covered in snow. They don't get very good correlations in those areas. So it's probably a combination of the model struggling in areas that are hard to predict because of reflectance and some problem with the extraction of the AOD from the column at ground level.
The questions?
So you mentioned that you would be interested in information on the constituents in the PM, and you said organic carbon especially. So would you be fine with just mass of organic carbon, or what is the status? Do you need to know special, like a substance itself, or is it just mass?
Organic carbon would be a good step, definitely. I think the polycyclic aromatic hydrocarbons are one that comes up a lot in the toxicological literature, but I wouldn't expect to be able to get that on a first pass anyway. So I think that would be a good step. But again, it would have to be, I was talking to David about this morning, that some of these pollutants we probably don't need, just PM mass, a lot of that you're probably able to capture it pretty well at larger grid cell sizes without having a lot of variability within the grid cell. But that portion that's attributable to traffic, that seems to be so important in the health effects estimates, that's varying on 50 to 500 meter scale. So how do we calibrate our models so that we're predicting for those constituents which we think are active biologically and variable over space in small areas? How do you get that type of prediction meshed in with other predictions that are maybe more homogeneous? And how do you evaluate your model so that you can show that it's actually predicting at a scale where you know the true variation is occurring?
What about trends in emissions and trends in the models? It seems like these studies you need several years to run and to make sure that those trends get in there right.
Okay, let me see if I can just pull this up very quickly, because I thought this might come up, and I have a plot that might be useful. Hope I have that plot. Yeah, there it is. So what we're sort of banking on with these studies is that the trend, we might see trends going down, or even day to day, seasonally, we know that there are big patterns. But several pollutants do have, large area variation that's still meaningful. So, we do know PM and ozone have these big regional patterns that we've been able to show do associate with health effects. But the spatial pattern is often maintained over time. And this is an example of what I mean. So this is the inhalable particle network that was run for about 3 years with 51 cities by Environmental Protection Agency. John Bachman had the foresight to think this PM 2.5 might be important to health studies, and convinced the senior management at EPA to fund this for a few years, way back. And then here it is in 2000. And, the correlation here is not perfect, but think of everything that happened in that 20-year period, and recessions and huge amount of development shifting to the southeast and, Texas areas from the industrial heartland. But you still see a fairly good relationship that's maintained. So a place like Los Angeles was high in 1980, and it continues to be high. So what we argue in a lot of these studies, and it may not be perfectly correct, is that these trends are going down, but our rank ordering is something that doesn't change that much in terms of the exposure. Now, as we get into these smaller areas and cities, that probably is more problematic because, as roadways develop, new housing developments, the work that Christine does with Mike Kleeman looking at, suburban developments, it is going to change a lot. And, we can't argue that we're going to have the stability in the spatial pattern. But there are several studies that have come out of Europe and now one out of Canada that show, even over 7 to 10 year periods, they've gone out and laid down saturation monitors for NOx, at hundreds of sites within the city. You get these huge correlations, 7 to 10 years later. The levels have gone down. There's no question about that they've been consistently going down over many years. And that's a good news story. But are they changing the pattern? In most cases, we think not. In some cases, perhaps. But if it's just going down, it's linearly, we can scale our risk estimates.
But there's going to be confounding things here. Like, it's going to be sulfate that's probably dominating the reduction in these, where your organics are not.
You're right. And so we're not even touching the issue of the constituents here. And that, too, is another area where an atmospheric chemistry model would really help to inform our health effects assessment, because we could start looking at those changes in constituents and seeing whether or not those are correlated with the downward trends, or whether they're actually starting to change the rank ordering.
Thank you.
Yeah. Well, in this model, we're taking exposures at, a snapshot in time. And we're assuming because of this type of pattern that they characterize the entire period. So we're not taking into account seasonality. And in this health model, we're following people up by the year. We have looked at the question of whether or not more recent exposures are more important than the long-term trends. And it seems as though, if you look at, say, where we had the data in California from 1988 up to 2000 for NO2 at a lot of sites, when we look at that model, we do get significant effects for NO2 overall. When we deviate NO2 from its long-term mean, and we look at, say, the last 5 years or the annual fluctuation around the mean, it seems as though the long-term trend is still much more important for predicting the health effects, which is suggestive that there is some contribution to this formation of chronic disease that's going beyond sort of seasonal oscillations or fluctuations. But certainly there are a lot of studies that show the constituents change in the winter versus the summer, and the social spatial pattern also changes, right? So you're more likely to have your windows open in the summer, more likely to be outside exercising. So that's been one of the hard things with ozone, is trying to get a good exposure assessment of ozone that also takes into account that spatiotemporal change in behavior.
No more questions? Then please let us thank Michael again.